Hello everyone and a very warm good morning to all the professor and also good morning to all organizer committee and good morning to all my dear friends. My name is Kashif Nawaz Khan. I am the student of MSc Part 1 same semester 2nd. Today I am going to talk about my seminar topic collision rearrangement reaction. So here we see the contents of my seminar topic. So these are the contents of my seminar topic. First, I am going to explain each and every point in this seminar. Introduction, sigmatropic rearrangement, reactions, general reactions of collision rearrangement, mechanism and the characteristic, and lastly, I am going to explain the applications of the collision rearrangement reaction. So here we see the introduction of the collision rearrangement reaction. So collision rearrangement reaction, the collision rearrangement reaction is a powerful carbon-carbon bond forming chemical reaction. This is the carbon-carbon bond forming chemical reaction, and this reaction is discovered by the scientist respected Sir Rainer Ludwig Collision in 1912. And this reaction is a first sigmatropic reaction. Why it is called as the sigmatropic rearrangement? Because this reaction takes place under the sigmatropic rearrangement. So what is the sigmatropic rearrangement? So firstly we see what is the sigmatropic rearrangement reactions. So here we see a type of pericyclic reaction. So sigmatropic rearrangement reaction, a type of pericyclic reaction in which a migration of atom or group of atom with sigma electron from one end of pi system to another end of pi system. There is no any change takes place in the sigma and pi bond. Means the sigma and pi bond is remains same, but only the rearrangement is takes place. So what happen here? This is the example 1,3 sigmatropic rearrangement. So why it is called as the 1,3 sigmatropic rearrangement? Because here we give the numbering to this compound. This is the carbon number 1. It is the saturated carbon, and the carbon number 2, carbon number 3. This this hydrogen bond, that sigma hydrogen bond is break, and that bond is attached to this carbon number 3. Therefore it is called as the 1,3 sigmatropic rearrangement. And here this compound indicate that the breaking or making of the bond is takes place simultaneously. Therefore it is the concentrate process, and here the formation of compound is takes place. This is here is a new sigma bond is formed on the third carbon atom. So this is the sigmatropic rearrangement, 1,3 sigmatropic rearrangement. Then we see this another example, that is the 3,3 sigmatropic shift or the 3,3 sigmatropic rearrangement. So here we see how that reaction is takes place. So this is the compound. We use cyclohexadiene, cyclohexatriene. So what happened here, that compound is that compound is converted into the cyclohexadiene. So how that compound is takes place, how that compound is converted into the cyclohexadiene. So here we see the number, here we give the numbering to this compound 1, 2 and 3, 1, 2 and 3. So here the formation of sigma bond is takes place in between this and this carbon atom. That one bond is break, and here that bond is shifted in between this carbon atom. That bond is shifted here, and this pi bond is shifted here. This compound is indicate that the breaking and the making of bond takes place simultaneously. So this is the cyclohexadiene. This is the cyclohexadiene is formed here, and the new sigma bond is formed in between these two carbon atom. This is therefore it is called as the 3,3 sigmatropic shift or the 3,3 sigmatropic rearrangement. So this is about the sigmatropic rearrangement. Then we see the general reaction of the collision rearrangement reactions. So here we see this is the first reaction which was discovered under the sigmatropic rearrangement. As I was told you, this reaction is also called as aromatic collision rearrangement. Why it is called as the aromatic collision rearrangement? Because here is the formation of product, that is a aromatic product. Therefore it is called as the aromatic collision rearrangement. When aryl allyl ether heated and it gives ortho allyl phenol. This reaction is indicate that when ortho allyl phenol is required a more energy in the form of heat, and that particular compound is formed here, that is the phenol, and it is the aromatic compound. So it is the most stable compound. How this reaction is takes place, I am going to explain in the mechanism. So here we see the mechanism of the collision rearrangement reaction. The ortho rearrangement is concerted process. Means this is the concentrate this is the concerted process, and this is the concerted process. This is the concentrated process and it follows cyclic mechanism. It follows the cyclic mechanism which proceed through the formation of cyclic six-member transition state in which the repurchasing of oxygen allele bond and is synchronous with the formation of carbon-carbon bond at on the ortho position. Means the formation of the bond is take place on the ortho position. Thus, there occur the formation of cyclohexadiene which convert to the more stable aromatic compound, that is phenol. I was told you. I was already told you the product is formed, that is the phenol, and that is the very most stable compound. Here we see the mechanism, how the reaction is takes place. So here I am going to explain the mechanism. So this is the allyl ether. What happened here? Here we give here I give you the numbering of this compound, that is 1 2 3 and 1 2 3. That two atom is the saturated atom. So therefore what happened here, that one bond is break and that compound is attached on the ortho position. Therefore the formation of ortho allyl phenol takes place. But how the phenol is formed? So here we see that is the double bond is formed and here is the hydrogen is available. That hydrogen is shifted here, migrated, and the tautomerizes this hydrogen and this bond is break like this and the formation of phenol is takes place. Here we see the ortho allyl phenol is formed, but here is a para phenol is also formed, but generally ortho allyl phenol is formed because here the hydrogen is easily available for the migration or the tautomerization. Therefore the ortho allyl phenol is the general product of the Claisen rearrangement reaction. But when we block these two positions of that compound, ortho positions of that compound, here is no hydrogen is available for the migration. Therefore that bond is break and here is attack on that para position and the formation of para allyl phenol takes place like this. Okay, and this bond is break like this and hydrogen is shifted from here because the hydrogen is available. But ortho allyl phenol is the general product because hydrogen is easily migrated from here to the oxygen. So this is about the mechanism of the Claisen rearrangement reaction. Then we see the next point, that is the characteristics of the Claisen rearrangement reactions. So here we see the characteristic. It is the sigmatropic rearrangement reaction. As I was told you, this is the sigmatropic rearrangement reaction, and because here the rearrange the sigma bond. This is one step mechanism without intermediate. There is no intermediate is formed or any charge. Claisen rearrangement does not need a catalyst and it follow first order kinetics. No cross product is formed. No cross product is formed because because this is the intramolecular reaction. This is the intramolecular reaction. The rearrangement of the bond takes place inside the molecule. So this is about the characteristic of the Claisen rearrangement reaction. And then we see the last point, that is the applications. So here we see the applications of the Claisen rearrangement reaction. The Claisen rearrangement reaction applicable to allyl etherphenols, and how it is applicable for the Claisen rearrangement reaction. Here we see the rearrangement of bonds takes place. What happened here, that is the carbon number 1, carbon number 2 and carbon number 3. Here that one bond is break and that group, allyl group, is attached on the third carbon atom, on the third carbon atom, because 1 2 and 3 and this type of product is formed. So therefore it is applicable for the allyl ether of enols. Then we see the rearrangement of allyl amine oxide. Oxygen atom of allyl ether is replaced by the sulfur. Synthesis of orthogonal volatile oil and desynthesizes. So this is and carminative. So this is all about the important applications of the Claisen rearrangement reaction. Here are these are the references I have used for to collect the matter of that particular topic. Modern Organic Chemistry by M.K. Jain and S.C. Sharma, and this is also the second and third reference is also used for to collect the matter of that particular topic. If you have any doubts and queries, then ask to me. Here my seminar is over. Thank you so much for watching, and here my seminar is over. Thank you so much for watching and listening carefully. Thanks a lot.